3 minutes max, the
Sure.
presentation. So.
Just send me some slides. Is it a slideshow or is it?
It's just one slide. It's just like a QR code, and then I'll just demo like 2 minutes, and then I'll show the QR code right after.
Columbia lost 400 million federal funding. That's not good.
They're protesting right now.
Oh, that's what it's.
Yeah, yeah. Is it Jay?
Yeah.
Is it cool if I don't do a subject and stuff?
Sure.
I'm just sending it.
There it is. I'll leave this up.
Awesome. And then, can I get on the Zoom call real quick so I can look in?
Yeah, go ahead.
What's the link?
Go to datastructure.es. Structure.es.
Oh, like
Data structure.
Okay.
UR.
You
Dot es.
Okay.
Yeah. And then just click the zoom link. Oh, there. Test equal to 0. Turn on chat. How about now? Can people hear me now? Hello. Anyone here? Can anyone hear me? Yes. Okay. It's echoing. Ah, you just joined. Zoom. Oh no, go. Go ahead.
Um,
Walk over here. Sorry.
like many freshmen, I was frustrated with Berkeley dining. dining website last year. So this is mainly applying to freshmen. So if you're not a freshman or you don't eat at the dining halls, please ignore this, but it's a little presentation, little pitch. And so I created a neat little app called Oski Eats. I think it's pretty useful to anyone eating on the dining hall, so I wanted to share. So normally to check today's menu, I would go to the Berkeley Dining website. Let's do that real quick. And you wait for it to load. And this is already a little slow, and then select where you want to eat. It's not super user-friendly, and it includes breakfast, which is irrelevant at this point. And these symbols and nutritional information are almost impossible to understand. So Oski Eats brings Berkeley Dining directly to your phone. Now, I eat everything. I eat everything, but I know many students here have dietary restrictions. If you're a vegetarian or you have allergies, quickly, can we get a show of hands if anyone's vegetarian or you have some peanut allergies or milk allergies? Anyone? I see a couple of hands. The Berkeley Dining website can be difficult to navigate for you guys. So Oski Eats brings Berkeley Dining into your phone. With Oski Eats, you can simply select your dietary preferences and get a filtered menu every time. So say we're vegetarian and we have milk and egg allergy. You can save these preferences and you never have to set them again. When you tap what's cooking, you see the next meal period with menu items filtered to your preferences. Why wade through the entire Berkeley Dining menu when you can filter only by the items you can eat on Oski Eats? And for gym enthusiasts, as cutting season starts, tap the plus icon on the right side of the screen, and you can add menu items to your meal. You can adjust serving sizes and track your macros, including calories, proteins, carbs, and fats. And as we partner with Cal Dining, ASDC, and the residence halls, we're adding more features like cloud meters similar to RSF for dining hall wait times, nutritional information for all the on-campus eateries like Browns and GBC, and showing how many meal swipes you have left. And if all of that doesn't interest you, you can at least play Oski and Tree Fruit Ninja at the top of the screen. If you tap the bears, you get more points, and if you hit a tree, your score resets to 0. So I'm going to show the QR code really quickly on the screen. Give me a second. Oh, screen. There it is. Yeah, so here's a QR code. It just takes a second to download, and I promise it'll make your semester eating at the dining halls much, much easier. If you have any questions or comments, feel free to find me after or email me at aguilanks@berkeley.edu. Wanted to give a huge shout out to Professor Hug and Professor Iakoto for giving me permission to present. And thank you.
They want a meal preference for meat.
Oh, specific meats? Is that like chicken and pork, kind of like that maybe?
Yeah.
We'll definitely get that on.
And Android.
It is not on Android currently. We're working on that to make sure like we can get it to all students. But currently, it's just a iOS app because I only know Swift at this point. But you know, we'll get to other languages. So yeah.
All right. And
oh yes, sorry. We just leave it on for 30 seconds.
Yeah, sure. It's kind of like in the lecture, but it's fine. While we're leaving this up on screen, we can do kind of announcements. So homework 2, and I believe lab, I want to say 5, 6 is due today. How's everyone doing on that? Homework 2 good? How many people are still working on homework 2? All right, no worries. Still got some time. How about lab 6? Things going well? Sounds good. Other than that, For test cases, how many of you want to write? I cannot say that because it is not a number of test cases, it's how much coverage your test case. Right? Yeah, your goal should be to test every single possible thing that could go wrong. Just a set of cases that you practice. Yeah.
Thank you so much. Thank you, Professor.
All right. Other than that, I believe Project 2A is coming up due soon. So make sure you get on that. All right. We're starting a bit late, but that's fine. Let's get started right now, shall we? All right. So far, what we've covered is a few ideas on how you can make sets and maps. We used binary search trees, and then we improved them to 2-3 trees to make our sets and maps. We had an array version that wasn't really good, and then we had our LRBs as kind of our improvement on 2-3 trees. Now, if we look at how we can use these for sets of maps, right? The set version is very, very slow. It is way too slow for our purposes. It takes n units of time to find an item in it. So we're not going to like that. The BST's versions, once we get down to LRBs and guarantee sufficient like balancing, we do get log n runtimes. That's fairly good. But there are a few issues. For one thing, log n is good, but we can do better. For another thing, not everything can be put into a tree. One of the issues of the LRB is that we need things to be comparable. We need to be able to say something is less than or greater than something else. It's not always possible to like compare two things, right? Like, how do you compare these two Chinese characters? It's like comparing apples and oranges, right? Yeah, not really possible. So we're going to try to find a way to avoid that comparison necessity. And we're also going to try to beat our log n runtime. And that's going to be our main goal for today, writing a set implementation that takes constant time to run and which doesn't require things to be comparable to work. So let's just start off with just a simple, silly example, right? Data structures tend to be similar to things that exist in real life. And I like to like build data structures that I could build as a human. Like imagine that you as a human were trying to make a set, implement the add operation and the contains operation. How would you do it? To simplify things, we'll start off with just sets of integers. And we'll assume that we have only two operations. The add operation, which adds an item into the set, and the contains operation, which checks if a given number is in the set. Now, we're going to assume that if you add something, it's not already in the set, so you don't have to worry about duplicates for now. That you can always fix this by just checking if it's contained in the set first. So we can assume that that's fine. Our goal here is going to be to make these operations as fast as possible. So the first example that I might think of is just a write it on the wall set. I'm going to take a wall, like this chalkboard here, and I'm going to write down the number every time I'm asked to add a number. And if I need to check if something is on the wall, I just check all the numbers that I have to see if that number is contained there. This is very similar to how an array set might work. So I have two questions. Is it fast to add something onto this wall? How many people say yes? How many people say no? All right. Is it fast to contain, to check if something is contained in the wall? How many people say yes? How many people say no? All right. It seems like we're consistently saying that it's fast to add and slow to contains. Let's try and show that visually. Here I have an example of a set. And what I want you to do, for those of you on Zoom, is I want you to write an annotation of a 5 somewhere on the wall. Let's see how fast that goes. Let me check to make sure I have annotations on. Option. Can anyone do annotations? Enable annotations for others. Do not make me regret this. So go. Can you add a 5 to this wall? Can people? All right. You can't use it? What? I set annotations for others. No option. What? Oh, this is so sad. It's a webinar. But I said it, enable annotation. Oh. All right. Fine, I'll do it myself. How do you add a 5 to this wall? You draw it like this. All right, keep trying if you're on Zoom to see if it works. I don't know why it's not working. Can you try it now? Maybe? Now that I have annotations on? Nope. Oh well. Ah, well. Sad. All right. So it seems fast to add something to the wall. Uh, let's try adding it to a larger wall, shall we? How about this? Can you add this to the wall quickly? How do you do it? Just put the 5 down here. Yep. Fairly fast. Seems like it's fast to add things onto the wall. All right. Is it fast to check if something is contained? Let's check this. Is 439 on this wall? How many people say yes? Or actually, once you have an answer, say yes or no. Yes or no. No. Seemed fast? How fast was it? Was it fast to say no? Let's try bigger size. Let's try a wall of 100 numbers. Is 605 on this wall? Where is it? Yep, right here. How fast was this? Was this fast? No. Felt a bit tedious. Let's go bigger. I'm going to show you 1,000 items next time, and I'm going to ask you to find two things. One of them is going to be in the wall. One of them is not going to be in the wall. You ready? All right, raise your hand once you found it. All right, some people have found it. Keep going if you haven't. What's Zoom chat saying? Seems like some people on Zoom have found it as well. All right, so which one was it? The first one, white. Yes. For those of you who don't know Chinese, this is white, this is black. White is on screen right here. So, is this a good way to do a set? No, this is a terrible way to do a set. It takes forever to find what you want in this set. On the other hand, it was fairly fast to add things, right? So that does have that advantage. It didn't matter what type of items were, right? It worked just as well with integers as with Chinese characters or kanji. So how could we make this faster, do you think? Well, one option, you might want to sort the data, right? It does make contains faster, but add operations become slower as a result because you got to rewrite everything, move stuff around. It also doesn't really work on kanji because there's no really way to compare two Chinese characters next to each other. If you go down this path, eventually you get back to the tree set that we're talking about. The LLRBs, those are effectively what happens if you try to sort the data continuously. The other approach is to categorize the data. How do we do that? Well, we can do what I always like to do and go get boba. So I see some boba out, actually. How many people have been to TPT recently? Fair number of people. Have you noticed this thing on their counter? How many people have noticed this thing on their calendar? Few people. It used to be in front where like you could actually pick up the boba. Now they have it behind the counter. But effectively, the way that this works is that when you order boba, right, you get an order number. So you are number 13 or you are number 27. Once they make the boba, what they do is they're going to put the boba in the place corresponding to the last digit of that number. There's often 5 to 10 boba at a time. So you don't want to have like all the boba just lying randomly, because then it's hard to find which one belongs to who. So what they do is when you go to them, or when they make the boba, they see it's number 27. They put it in the 7 slot. And then someone comes up, says, I'm number 27. They go over to the 7 slot, and there's only one boba there. So they can get it and pick it up easily. It's very fast to add something, because you just need to put it down somewhere in the right spot. And it's very fast to find something, because there's only 1/10 of the area around to put stuff. So let's try to formalize this with a boba counter set. I have a wall. I'll split it into 10 areas, and I'll put numbers in the spot corresponding to that last digit. So we'll go through these same 2 questions. Is it fast to add? Is it fast to check if it contains something? Just before we get started, is it fast to add things? Yes? No? All right. Is it fast to contain things? Yes? No? Seems kind of iffy. Let's check it out. How do you add 5 to this wall? Yeah. The only thing you can do is put it in the bin corresponding to last digit 5. Is that fast? Seems fairly fast. You can add something to this wall of 100 numbers. How about checking if something's contained? Is 605 in this wall? Yes? No? Still figuring out? Yes. It's right here. Was this faster to find than the other version? Yes. Why was it faster? Huh? Yeah, you only have to look in one bin to search for the 605. So the speed of this, checking if it contains, is however large the largest bin is. Now, if the numbers are random, I just picked a random set of numbers for that. So it was about evenly distributed. So runtime will be reduced by a factor of 10. Are there any problems with this approach that you can see? Yeah. Huh? Yeah, the memory could be full. One of these bins could be full. Is there a way we can get around that? Yeah, we can add more boxes. As it turns out, we saw from our discussions of array lists that resizing can be done efficiently if you double the size every time. We can imagine doing something like that. Is contained still theta of n? For this one, yes, because you only have 10 bins, right? And eventually, you're just running n over 10, which is still n. But what if we increase the number of bins as we go further? If the number of bins stays constant, then we are going to be stuck at theta n. But if we increase the number of bins as time goes on, maybe once we have 1,000 numbers, we switch to using the last 2 digits, so we have 100 different bins, then maybe that might work better. That's a good point. Let's try and think about that next. Any other concerns here? Yeah. Huh? Yeah, if you want to add 15 now, do you want to resize all of the bins or just the 1 5 bin? That's a good question. Think about that as we go forward. We are going to try and address that. Yeah. So, was there someone said my name? All right. So we do have a bit more wasted space. We do want to minimize this. We do want to try and increase the number of bins. And one other thing that's an issue is there's not an easy way to do this with kanji right now, or Chinese characters. We don't have a way to classify Chinese characters. We'll worry about that last one later. Our goal first is going to solve some of these first problems. So now that we've gotten kind of an intuition behind things, let's try and formalize this with an actual program. The way that we're going to do this is we are going to create a linked list for each of these bins. That solves the problem of using too much memory, right? We just increase the size of a bin by 1 every single time. And our goal here is we're going to just create 1 bin for every single last digit and fill them in as we go. To check if something's contained, we got to look through everything anyway. So linked lists don't add additional runtime. Normally the issue with linked list is you have to look through everything to find something. But with the set, you have to look through everything to find something anyway. We do use a bit of wasted space here, but that's fine. It's minimal overall in the grand scheme of things. If you have n total items and m bins, then if things are equally distributed, then each bin will have about n divided by m items. So if m is constant, let's say we only have 10 bins, then we'll have n over 10 as our runtime. Theta n over 10 is the same as theta what? Theta n. Yes, because we get rid of any constant factors. So m being constant is not a good idea here. What we can do is make it so that m constantly grows as n gets bigger. So that does mean that we'll need to categorize numbers into m groups for arbitrary m, right? When I say the last digit of a number, you can only split it into 10 groups. It's impossible to split that into 15 groups or 20 groups or 100 groups. Do you have a way that you can split out numbers into roughly equal groups of any arbitrary number of them? Modulo? Yeah, that sounds like a good idea. In effect, the modulus operator is what happens when you divide by the number and take the remainder. So you can apply this to any value of m, and it will evenly distribute random numbers. It actually has a lot of other useful properties that you'll see in CS70. One useful thing is that relatively prime moduli are statistically independent. So if you decide to take something that's mod, let's say 5, and then switch to mod 7, even if mod 5 was bad, everything got stuck in one bin, chances are mod 7 is going to evenly distribute things. Same is true for any relatively prime numbers. So I don't know, 1,000,009,000 and 1,000,007. Those turn out to be relatively prime numbers. They're both prime, actually. And if you just swap between the two, you're going to get entirely different patterns of like how big each bin is. Another useful property is you multiply the size of m by an integer. Then each bin splits independently. So the numbers that are 1 mod 5 are all either 1 mod 10 or 6 mod 10. So if you try to take 5 bins and split them into 10 bins, then kind of each bin splits in half instead of having to worry about one bin moving on items to some completely different bin. So there are other reductions that are possible, but just for the purposes of this class, the modulus operator is the most natural and the best reduction function that you'll be seeing. We'll be discussing a few other options, I think, later. But this is kind of the one that's like the golden standard for this. To keep constant time contains operations, we need n divided by m to stay less than some constant. So there's a few approaches. One approach is that we increase m when the largest bin exceeds a certain amount. That's going to lead to a lot of empty bins in the worst case. Like imagine that all the numbers just happen to be divisible by 10. You're going to get a lot of bins. But it is going to guarantee this runtime. In practice, we don't use this too often just because like more often than not, it's just not as helpful. The other option is that we increase m every time the average bin exceeds a certain k value. And that's what we'll be looking at today. Now, how much do we want to increase the value of m? How many people want to increase it by some constant amount? Add a small amount. How many people want to multiply by a certain amount, like double the size? A lot of people are saying doubling. Why do we want to double? Huh? Yeah, doubling is very infrequent. And every time we need to resize, we got to move everything to a new spot. It's going to take a lot of time to do that. We want to minimize those. As we saw from our list versions, these operations, as long as we do multiplicative resizing, you can get constant amortized runtime. So on average, theta 1 time instead of theta n time on average. So we're going to be doubling m every time we do a resize. Let's take a look at an example. For this version, I'm going to say n divided by m is going to be greater than 1.5 every time we want to do a resize operation. So we'll be doubling m every time n divided by m exceeds 1.5. And we'll start off with an m equals 4, so we have 4 bins. I'm going to start by adding 7. If I add 7, where does it go? 3. Why does it go in 3 bin? Yeah, 7 divided by 3, or 7 divided by 4 is 3 remainder. If we add 16 next, where does it go? 0? Yep, because 16 divided by 4 has a remainder of 0, so it goes in the 0 section. What next? Let's add 3. 3 goes in the 3 bin. 11 goes in the 3 bin. Why? 11 mod 4 is 3. 20 goes in that bin because 20 is divisible by 4. When we add the next item, what's going to happen? When we add 13, n divided by n hits 1.5 finally. That's too large, so we're going to try to double the size of this array. Now we'll have 8 bins instead of 4. And we're going to have to move everything into a new bin. So where does the 16 go? What bin does it go in? 0? Why? Yep, 16 divided by 8 is 2, remainder 0. So it's in the 0 bin. Where does 20 go? 4. Where does 13 go? 5. 7? 7 goes in the 7 bin because 7 divided by 8 is 0, remainder 7. 3? 3? 11? 11 goes in the 3 bin as well, yes. So once we do this, here is our new structure. And now our n divided by m is back to 0.75. That's less than 1.5, so we can keep adding a few new items until we hit 1.5 again. Now, the data structure that's been built here, we might call it a dynamic array of lists set. It's kind of a weird name. It's not as intuitive our original idea, but the core idea kind of stays the same. As long as we have n items that are evenly distributed, the length of each list is going to be n divided by m, which is constant asymptotically. So operations will be constant on average. You'll need to check a small number of items for each bin. If I wanted to check if the number 9 is in this, for example, what can I do? I just look in the bin 3 because I know it's going to be in bin 3, and there's only 2 items to check, so it's going to be very fast for me to find things. Now, we'll think a bit more carefully about the runtime a bit later, but for now, let's try and solve some of the other problems we had issues with. One of the concerns I had was this only really works with numbers right now, right? So how can we get this to work with, let's say, lowercase strings? So let's say that I want to store the word cat. How might I do this? What bucket do I want to put cat in? One approach is we might use the alphabet as a bucket list, right? A is like the 0th bucket, B is the 1st bucket, all the way down to Z is the 25th bucket. So the word cat goes into bucket 2 because C, the first letter, is the 2nd letter of our alphabet if you start from 0. Now this does force us to start with 26 buckets. And after resize, what we can do, maybe we can take the first 2 letters. So that way AA becomes 0, all the way down to ZZ becoming 675. Seems like it might work. Anyone see any problems with this approach? Yeah. Well, we are going to have a lot of buckets. It depends on when we decide to resize. But generally speaking, if we're trying to resize like around when the number of items is sufficiently large, we're not going to get too much additional memory cost from adding a ton of buckets. Yeah. As long as most of our buckets are full of stuff, we're not using too much memory. Yeah. Any other like concerns you might have with this approach? Yeah. Yeah, not many things start with ZZ. Uh, yeah. I think there's like one word, like Zizix. This is a word. But not many things start with ZZ. Yeah. Anything else? Yeah. The number of bins are growing exponentially, but we said earlier that that's actually a good thing because we only want to do multiple kit resizing. Yeah, that's fine. There is some issue though with the bucket resizing. You have an idea?
Our base is based on the amount of letters that we have, so if we say under alphabet, our base would be really big.
Yeah, our base is base 26. I don't really like base 26 too much. Like, imagine if I wanted to do this with Chinese. I do not want to start off by having 40,000 distinct bins because there's 40,000 distinct Chinese characters to start with. Yeah. Any other concerns here? Yeah, in the back. Oh yeah, where do I put the one character words now? Especially once you start off with after the first resize, where does that one character word go? Does it go in the bin 0? Does it go in bin 26? Does it go in a separate bin? That's probably something we can fix, but it's still a really weird thing that might occur. Yeah. Here's kind of my answers. Yeah, where to put the short strings, that's probably fixable, but it's weird still. The other thing is it feels wrong for the strings to force our set to resize at 26, right? We kind of need to make an entirely new string set class instead of using our generics, because now our set relies on the fact that we're dealing with strings. We don't want to do that, especially once we start dealing with other objects, especially objects that don't necessarily split into 26 distinct bins. Like, I don't know, if I have a set of dogs, how do I define the first letter of a dog? I guess the dog's name. How do I define the first letter of what doesn't have a name? I don't know. Anyway, the big problem is that set was the one responsible for figuring out how to categorize strings. Intuitively, I don't want the set to be the one to decide how we categorize things, right? The strings are the things that know what they are. The strings should figure out how they categorize themselves. Because the set, it doesn't need to know about every object in existence. It should know how to categorize stuff. And at the same time, set shouldn't be beholden to the string class. The string class can't say, you set class, you need to have 26 bins. And the set shouldn't say, you string, you need to be in bin 0. It's kind of like a separation of work here. So one way we can fix this is, let's say that the set only sees integers. The set was the most flexible when working with integers because we have that modular arithmetic available. So we're going to say sets only work on integers, and everything else needs to have some way to convert themselves into an integer. So strings, you need to have some way to turn yourself into an integer if you want to be used in this set. What I'll do as a set is I'll take that string, ask the string to turn itself into an integer, and then I'll read that integer and decide based on that which bin to place the item in. That way, strings can decide how they get categorized. Set gets to decide when it wants to resize. What about other objects? Yeah, all other objects, we need to make them turn into integers somehow. It's up to that object type to decide how they turn into integers. And depending on how that works, it might make sets faster or slower. But the set doesn't need to worry about that. Yeah. Dot two string, dot two integer, that is a good idea. That is a potential option for any object. But maybe some objects want to do something different than just dot two string, dot two integer. We'll see. So how do we do this? How do I convert cat into a number? What do you want to make cat into a number? Any ideas? Yeah.
I mean, we already know it's stored as a number in our computers. We just represent it as like the hexadecimal or whatever.
Ooh, we know it's stored as a number in our computer, so we could just take that binary representation. That is a good idea. It is actually an improvement on an idea that we'll be talking about here. So we won't cover that idea, but it's a good idea. AES is not in scope, no. That is considered a cryptographic hash, which has different use cases than this type of hashing. In this particular case, we don't care about one-wayness as much because we're focusing more on like efficiency. You can talk to me about it later, and there is good talk about that. Yeah. Any other ways you can turn this into a number? Yeah. Take its length. It's a good idea. Yeah, I forgot this is yeah. A yes, I guess. And then you mentioned ASCII binary value. Yeah. Any other ways you might turn the cat into a number? All right, that's fair. Here's the kind of ideas that, oh,
Take the position of each letter, like C would be 3, A would be 1.
Mhm.
You just put those numbers next to each other as digits.
C turns into 3, A turns into 1, T turns into 19. So that turns into 3119, something like this. That seems like a good idea. Yeah, we could maybe do something like this. So here's kind of the ideas that I wanted to think about. Ideally, I want evenly distributed strings. We don't want any integer to have significantly more associated strings than average. If you just look at the length, are there words, is there an issue with like distribution? Some lengths are more common than others. Yeah, I think 3, 4, 5 letter words are more common than, I don't know, like 15 letter words or 246 letter words. ASCII binary value, this approach, I think those might actually be more distributive. Here's the kind of idea I would use. I kind of treat it as a base 26 number. So I take each letter A1, Z26, and then I turn each letter and multiply it by 26 to the power of some amount. It's kind of like this approach where you concatenate it, except in this case, we don't want to deal with like base 10 here, right? This uses base 10 a lot. I don't want to deal with base 10 because 10 is kind of a weird number to use in the computer. So here I use base 26. And this way I can like kind of turn this into a number. Why this specific pattern? Specifically, if you look at kind of how decimal works, right? Decimal has 10 digits, 0 through 9. And if you want to represent numbers larger than 9, we use a sequence of digits. The number 7,091, what it means is we take the 7, we multiply it by 10 to the third power. We take the 0 multiplied by 10 squared. The 9 you multiply by 10, and you take the 1 multiplied by just 1. And then we add those together. That's kind of the meaning of 7,091. And to write it, we write the digits 7091 in that order. The system for strings is kind of the same, but with letters. As you see here, right? This is just the first letter times 26 squared. 1 times 26, 20 times 1. And that adds up in the same way. Now, there is one difference. In decimal numbers, we have 0, 0, 0. That's the same as the number 0. But strings, as AAA is different from the string A. As it turns out, you can fix this. We just don't have a 0 in the system. That's why we started with A equals 1. It's a bit tricky to show why this works perfectly fine. You can try to convince yourself about this after class. But it turns out it works. So let's give an example. How do you convert the word B into a number using this approach? B is the letter 2, E is the letter 5. Feel free to work with a partner to do the math. All right. All right. Let's bring everyone back. All right. Did anyone get an answer? Yeah. 1487. Well, what happens if there are more than 26 characters? We'll come into that in a bit. 1487, I'm not sure if that's right, but that seems around the right amount. Did anyone just get like an equation to solve? Yeah.
I got 57 times 26 plus 5.
57 times 26 plus 5. That sounds very complicated, but I think it's right. Yeah. You kind of do this, and you get 1487. Nice. Yeah, good mental math. So as long as we pick a base greater than 26 for this, the algorithm is guaranteed to give a lowercase English word a unique number. Using base 26, no other word is going to get the number 1487. Again, this is a bit tricky to prove fully, but you can talk to me after class if you want to talk about this more. So using this, we're able to turn any string into a number, and then we can use our original hash setting idea, reducing it by mod, to get to a particular bucket. Now strings can figure out how to categorize themselves. The set can take numbers and categorize them how they want, and can decide when to resize. Now, there are a few problems with this. First off, I only can use lowercase letters for this, but that's not all things. What if I want to write two-pack or egg? If we want a unique integer for every possible string, then now I need to assign an integer to all possible characters. Like, what integer is corresponding to the exclamation point? Now, as it turns out, it's already been done. That is the ASCII standard. Here is the ASCII standard. It's kind of the most basic way that characters are stored in your computer. If you write out a character lowercase b, internally your computer is seeing it as the number 98. In fact, it doesn't even know that it corresponds to the lowercase b. It was just told that if you look at the number 98 and want to write it, it looks like a lowercase b to us. So these are kind of the numbers for the standard characters. As it turns out, you can use this directly in your code. Like if you decide to do char c equals 68, that works exactly the same as the character uppercase D. You can do subtractions and additions and things with characters, and that actually has some use. We'll talk about that more in 61C, actually. For English-only text that includes punctuation, the maximum is 126. So you can use 126 as our base to ensure unique values for all possible strings. If you want to go into other things, like these, they have other values. We can use a form known as Unicode, which encodes a lot more characters. Like this Korean character is number 54,812, which is really big. If I really wanted to, and I wanted to do like Japanese kanji, for example, the maximum possible value is 40,959. And if I wanted to turn, for example, my name in Japanese into a number, then I can do that. I can take this string of 4 kanji, and I can evaluate it kind of as a base 40,959 number. It turns into this giant number, which is million, billion, trillion, quadrillion in quintillions. It's a huge number, but it works. Here's my name. Right before me is this, and right after me is this. I'm not even sure that's actually a character used in common Japanese. I think it's mostly in Chinese. If you're curious, the last character is this, but the idea is you can kind of turn any string of arbitrary Chinese characters into a number using this. Is this a good idea to just keep going? Not really. For one thing, this is a big number. This number actually doesn't exist in Java as an integer because that takes too much memory to store. In fact, the integer values of this grow exponentially with the number of characters you have to deal with. Even if you limit to just haiku, which are what, 17 characters long, you'll get numbers in the quinvigintillions, 10 to the power of 78. Nowhere near something that you're wanting to store in a computer. Now, Python does allow you to deal with arbitrary precision, arbitrary length numbers, but on actual physical computers, you'll not actually be able to store them. Python does some trickery under the hood, and it makes it really slow to work. So we're going to deal with Java. where in Java, the largest number that exists is 2,147,483,647. And if you try to increment that by 1, you go down to negative 2,147,483,648. These two numbers are plus 2 to the 31 minus 1 and negative 2 to the 31. You don't need to know these numbers exactly. Just know that generally speaking in Java, numbers range from negative 2 billion to positive 2 billion. So because of that, we won't get the numbers that we expect. In base 26, even for short strings, you're going to run into this overflow. So if you take this into omens, you'll get this 28 billion number. If you tried converting it to ASCII directly using base 126, you'll actually get the number negative 1,867,000,000, etc. This is not the right number because you can't multiply a bunch of positive numbers to get a negative number, but it is the correct number in a Java sense because it's the same number modulo 2 to the 32. Now, the official term for this is hash code. In effect, what we're doing is we're taking things that could be anything, really, and turning it into a number that is a fixed size. In this case, a number somewhere between negative 2 billion and positive 2 billion. Our integerization function effectively is a hash code because we're taking any arbitrary item and turning it into a number between those two bounds. There's only 4 billion possible numbers it could possibly be, and that's the fixed constant size set. Now, because of that, you can't make unique factorizations for each string. Instead of base 40,959, Java decides to use 31. 31 has a lot of good reasons. There's a few extra slides, and you can talk to me about it later. But effectively, it's just a number that's nice to use. That does mean that we are going to get things with the same hash code. So I can turn this into a number, 839 million. You can actually try this on your computer yourself and check the hash code. Strings have this hash code function built in. Of course, there are other strings that can map to this. This string that I found, plus or minus capital E, lowercase r, lowercase e, capital W, lowercase n, happens to also match with my name. But it was very hard to find this. Generally speaking, you're not going to have multiple strings with meaning that happen to map to the same thing. Not easily, anyway. Once we do that, we effectively get what's called a hash table. The idea is every single thing knows how to convert itself into a number via what's called a hash function. And then the set, all it does is it takes that object, asks, hey, can you turn this into a number for me? It takes that number, it takes it mod some amount, and it'll put it in the right bin. And you can kind of see where things go. My name gets put here if I'm writing in English. 2 if I put it here. There's a few random Chinese things here in Korean, something in Arabic. Parent cow got inserted into this set last semester and didn't get removed. Bees, dogs, some Farsi, I think. No, not Farsi. Hindi, sorry. Yeah. So we can do these things. Now, there are other versions of hash tables, but this is the one we'll be talking about in this class. Just like trees, you can kind of come up with a new idea and show why it's better in some obscure way. So everyone likes to do that and make an entire research paper out of it. It's very fun to read a bunch of them. Now, in Java, these are the most popular implementations for sets and maps. They're really good in practice because we increase the number of bins with the number of items. On average, every single item takes a constant amount of time to find and takes a constant amount of time to add, assuming your hash function is constant time. It doesn't require items to be comparable, unlike trees, and the implementations are often relatively simple. In fact, if you look at a Python dictionary or a Python set, they're actually just hash tables in disguise. The Python does make this under the hood. Now, how do you know an object's hash code? You might think from like comparables, right? To compare things, you needed to implement comparable as an interface. Fortunately, you don't need to do that for hash codes. Instead, this hash code is so ubiquitous that it is one of the few things that all objects need to be able to do. In fact, here's a list of all the things that objects need to do. ToString and equals we discussed earlier in the class. Those seem fairly like standard. Everything needs to turn into a string so you can print it out. Everything needs to be checking if it's equal, so you can do equals equals. Hash code is so important. That's the third thing that we're forcing you to do. Everything needs to be able to turn into an integer. By default, it is actually kind of the how it's stored in memory. For reference types, that's actually the pointer. And everything has a pointer, so everything can be turned into a number. Yeah. These others, we're not going to discuss in this class, but here are kind of like a bunch of other object operations. Now, Java's actual hash code is below. This is the actual code, and you can test it out on your own to see how it works. And here's a few other examples of how this works. Apparently, we were able to find two things that make sense. At least I'm assuming this Korean makes sense, right, Josh? Oh, so this is Josh Hug's name in Korean, and this is Kamala Life Blue. Yeah. Now, one minor caveat, if you want to put -1 here, ideally you want to put in the 3 spot, but modular arithmetic doesn't work like that in Java. For some reason, it likes to say that -1 mod 4 is -1 instead of +3. You can kind of go over this to feel why, but I personally like thinking that -1 mod 4 is 3 instead. So you kind of just have to use this floor mod operation. It's annoying, but it works the same way as modular arithmetic. Yeah. Overall, you get a fairly good hash table. As long as the items are evenly spread out, it's fairly good. And you can get constant runtime for everything. Now, again, operations can cause a resize, so it's amortized runtime, and you assume an even distribution of items. So it is dependent on that. But after all those caveats, you get a set object that is constant time adds, constant time contains, and we have beaten our binary search trees. This is the best possible we can get. And this is kind of the golden standard for tables, sets, and maps that we'll be discussing in this class. All right. How do you exactly, which two things have to say? Well, we don't use the hash code to decide we just use the hash code to decide. So that way, you have to be with the data. They'll always say, but when we look for them later, we expect to see.
I gotta go to a meeting. Like 26. One 26. Like created it.
But like if you try to you realize that and then the first 2 digits which is 101. Yeah.
So you could just use any set of consecutive numbers. If you do 3 and like,
I think you miss some numbers if you do that. I don't think you will this sort of game. But you can try it out, see what. Yeah. It is a bit kind of like stating there.
is there any advantage to like 1 through 26 over like 0 through 20?
The main advantage there is that you get like a separate from A, right? If you do 0 is A, then A and any sequence of A's is the same number.
Mm-hmm.
Sure.
I think.
Yeah, sorry.
Oh no, also I think you mentioned that there are like other like papers on different methods that people use for hashing. Are there any ones that you recommend?
That's I actually don't. So you can kind of look them up. I personally like them on Wikipedia. Yeah. The idea is when you have a dice, right, and there's already something you can do, take that item out. And the idea is as long as you have enough sequence around, that only happens. And then you can show experiment. You can prove that about, and you prove experimentally it's fine.
I'm just curious on why it's 31 per job.
Yeah. So there's a lot of good reasons for this. The first reason is that 31 is a prime number.
That's what I was thinking. Yeah.
Yeah. And prime numbers, they're nice to use. You don't want to use an even number because numbers are mod 2 to the 32 in Java.
Gotcha.
And if you use an even number after you use 32 characters, all the numbers are multiples of 2 to the 32, and that's bad. So 31 is prime, so it ends up evenly distributing things. The other good thing is that 31 is 1 less than a power of 2.
Okay.
As it turns out, multiplying by a power of 2 is really efficient.
Yeah. So then you can just go up easily and subtract 1.
Yeah. The way that it works is you know how in like standard decimal math, right? Multiplying by 100 is really easy because you just add 2 zeros at the end.
Yep.
In a computer, multiplying by powers of 2 is easy for the same reason. You just add 5 zeros to the end of your binary.
Binary, it makes sense if it's all.